Hi everybody, welcome to another video in Calculus 2. We go to section 10.5 this time. So previously in section 10.4 we have three tests for convergence or divergence. The first one is divergent test. If the n terms go to 0, inconclusive. If the k terms where k go to infinity not equal to 0, that is divergent. The first test. The second, we have the integral test. The function is continuous, positive, and decreasing. But in my MATLAB homework, there actually will be 4 of them. And another one is we let the function equal to sequence. So when those 4 satisfy, then the behavior of a sequence, the behavior of a series is the same as the behavior of the integrals, meaning that both of them converge or both of them diverge. However, the values of the integral is not the values of the series in general. And then we have, it's not really a different subsection, but this is rather important. What we have is the P-series test. So this is called the P-series test. And we use this quite a lot. So the P-series in this form, if P is greater than 1, convergent. If P is less than or equal to 1, divergent. Right. So those are three tests we have in section 10.4. Right. Just want to go back and go over everything. And on that note, I actually make a mistake when on the section 10.2. So the part here, this is obvious. Actually, I changed this in the note and I post the correct one because there's overlapping here. So obviously we have r to the n, the geometric sequence. If r is equal to 1, then we have 1 raised to any power, so it's just 1. So it does not exist only when r greater than 1 or r less than or equal to negative 1. Right. And this should be precisely if we add r to the n, and this behavior is as n goes to infinity. Right. So we have that, and so we have to change this here. So the divergent is not including the 1 because the 1 is including in the convergent interval. So that is the square bracket convergent at 1, but when greater than 1 is divergent. Sorry. Yeah. So this is obvious because when r equal to 1, we just have a sequence of constant 1, and that's certainly convergent. So yeah, and of course there's overlapping that makes no sense at all. Right. So yeah, just need to make that correction. Anyway, now we go to section 10.5. So in this section we would have 2 more tests in testing if a series is convergent or the series divergent. Right, 2 tests, and both of them called a comparison test. The first one is limit comparison test. The second one is comparison test. When I took calculus 1, this is called direct comparison test. So I thought I would add that here too. So this is also called direct comparison test. Right, let's look over the theorem first. Let series A sub k and B sub k, those are series with positive terms. So this is quite important. Only works if the terms are positive. Now, if because they're positive, so that's not really important for the 0 here, but if b of k is greater than or equal to a of k, then and b of k is convergent, then a of k is convergent. And if b of k is less than or equal to a of k and b of k is divergent, then a of k is divergent. So what it actually means, think about this. When with the way we write this, if we try to put something that makes more sense, even though mathematically it's not perfectly right, but like I said, it's easy to understand if we say if b of k is convergent, anything less than convergent is convergent. If b of k is divergent, anything greater than divergent is divergent. So in this note, I only write anything greater than or divergent anything greater than divergent is divergent. And anything less than convergent anything less than convergent is convergent. So, right, this is easy to understand. So now, so that's pretty much what this theorem is about. The comparison test, what we actually compare to, well, that's difficult, right? Usually when we have the problem only give us one series, we have to come up with another series to compare to. So the first question we should ask is, what do we compare to? And this one is, the answer is, well, like I said, it depends. And so this test is actually this test is one of the most elegant tests out of all those tests, and also is one of the least practical one, because this test, the direct comparison test, we usually use that when we already know the answer. We already know if this series is convergent or divergent, and then we use this test just to show that it actually is convergent or divergent. We should already know that if it is convergent or divergent already. We just need to use this to show it actually is. So I'll write this. Direct comparison test, this one we usually know if the series is convergent or divergent already. We just need to use this to show it actually is. So usually we know if a series is convergent or divergent already. We just use this to confirm it. To confirm that it is convergent or divergent. That's what the use of this test. Because of that, it is elegant, but not very practical. Right. So let's look at this. The first example, is this one convergent or divergent? We'll just take a wild guess. Of course, we have the answer here already. Right. So when we have this one over k squared plus 10, if we don't have the plus 10, then this is a P series that is convergent because P equal to 2, convergent. Now if we have the 10, what happens if we make the denominator slightly bigger? Then the whole thing is slightly smaller, right? So this is what we start. So we have that, and what we do is we compare two. We will compare to the series 1 over k squared because that's reasonable. They are the same, right? Now, and then we have 1 over k squared plus 10. If we add 10 to the denominator, the whole thing getting smaller. So this one is actually less than or equal to bigger denominator, smaller quotient. So that one, this one less than or equal to that. Now, this one is a P series, which is convergent. So it is convergent. Anything less than convergent is also convergent. So usually when we come up with the series to compare to, the rest very easy to prove. But or n doesn't matter. This one is convergent. Because P series, P equal to 2. And if P is bigger than or equal to 1, then it is convergent. That's why I review before we actually go to this section. So if P is greater than or equal to 1, it is convergent. Now, this one is convergent, and that is less than it. So it is also convergent. So we have this relation, anything less than convergent is convergent. Is also convergent. So that's nice enough, right? Now the next one. Can we do the same thing though? Can we take out the 1 and we compare to that? Then yes, yeah, of course we can. But if that is the case, what do we have? Now, think about this. If don't have the 1, I'll just have some scratch paper here. If we don't have the 1, then we have 2k cubed over 2k to the 4th. Simplify, and we just have k. 1 over 2k, right? And what's that? Now if it's actually a series, then we can take the 2 on the outside, right? What we have here is a P series where P equal to 1. If P is equal to 1, it is divergent. And also when P equal to 1, this is called the harmonic series. Harmonic series is divergent. Right. So If we take out the 1, we have a divergent series. Does that work? Right. And then let's just compare. So we know this one is divergent. Now which one? Compare this with this. Which one is bigger? Now, the same reason here. The bigger the denominator, the smaller the quotient. So compare those two. This one has the bigger denominator, so it's the smaller quotient. Right? Same reason. Right? Now, once again, bigger denominator, smaller quotient. Right? Now, and we know this one is equal to 1 over 2k, and the series contained in this term is divergent. If it is bigger than divergent, then it certainly is also divergent. So that's good then. So this certainly works. Right? So let me write out. Compare to this series k cubed over 2k to the 4th, which is equal to the series 1 over 2k, and where we can take out the constant. And this series is divergent because of the p series p equal to 1, or because it is a harmonic series, it is divergent either way. So we have this one divergent. So if it is divergent, multiplied by a constant is still divergent. We say p series p equal to 1. So anything less than equal to 1 is divergent. So we know the whole thing is divergent. Then we just properly write k cubed over 2k to the 4th minus 1 is greater than or equal to k cubed 2k to the 4th, which simplifies to 2k. And the series contained in this term is divergent, and it is bigger than divergent, so it will be divergent. So because of those two, the original series is also divergent. But then you say, what happened if instead of a minus, if it is a plus? If it is a plus, then we have to flip inequality like this. Now, if it is less than divergent, then we cannot say anything. Again, bigger than divergent is divergent, less than convergent is convergent. If it is bigger than convergent, we don't know what it is. If it is less than divergent, we don't know what it is either. So it have to be strictly this. Right. Now this one, what do we compare to? Now this is a bit tricky, right? So now in that case, I asked you. That's why this test usually we use it when we already know the answer, and we just use the test to confirm it. So take a look at this. By the way, there's the ranking here, right? So ranking says Ln, usually Ln is less than any power function. So Ln of k is less than any power of k, less than k, less than square root of k, less than k square. So which one do we use though? Do we use k? Do we use k square? Do we use k cube? Even, because Ln of k is always less than any power of k. Right. So the question is, we have Ln of k. It is growth rate is less than any power of k. So any power will work. We could choose 1, 2, 3, 4, 5, doesn't matter. It's always like that. By the way, because it grows significantly slower, it actually also less than or equal to. So any power will work. But what do we choose for the power here? So we choose 1, 1/2, 2, or 3. Right. Now, the trick here is, usually if this is the case, the smaller the better. So we don't want to choose 5, because if we choose 5, the top is bigger than the bottom, is not going to work. But like I said, I kind of know the answer already. So in this case, just say less than or equal to k. So we compare to k. That cancels out, and we have this series equivalent to 1 over k squared. And this is a p series. And p equal to 2, which is convergent. So by now we to see that most of the time we compare to the p series, or sometimes geometric series. We see that in the next part of the section. Right, so we compare to that, and then we see which one is bigger. Well, I did mention that Ln is less than any power of k, right? So Ln of k is less than or equal to k. So now when we divide by k cubed, it's going to be less than or equal to k over k cubed. And now we have the series of all these terms is convergent. So it's the anything less than that is also convergent. So this convergent, this is less than convergent, so it is also convergent. So yeah, so it's not that bad. Like I said, usually we know the answer already, and when the problem is convenient enough to do that. Like I said, if I change this to a plus, we cannot use this test, or it will be a lot more difficult. If I change this to a minus, it will be a lot more difficult to prove. So in terms of it's actually very elegant, but very, in terms of practical or not, it is definitely not. So if we have a choice, the limit comparison test will be a lot better. We work with the wider range of series. Right. So limit comparison test. So what's different here? So limit comparison test, once again, we're going to have two series of positive terms. So nothing different. But the reason it is called the limit comparison test, because we will take the limit of the two terms in a sequence. Now, if whatever the limit is between 0 and infinity, if it is finite positive number, then the behavior will be the same. Both of them will converge, or both of them will diverge. If L equal to 0 and one of them is converge, then the other one is converge. If this is equal to infinity, meaning that the top is if it is L, if it is infinity, then and B of k is divergent, then H of k is also divergent. Right. Now, if B of k is convergent, and this is equal to 0, which means the row rate of the top is even less than the bottom, right? If this is 0, meaning the bottom is bigger than the top, and that means if it is convergent, the top is also convergent. Now, if it is infinity, means the top is bigger, or the top grows faster to infinity than the bottom. And if the bottom already divergent, then the top is also divergent. So think about that as a row rate for these two. Hopefully we have one example like that. Right, next. Determine whether the following series converge or diverge. So now when we have something like this, it will be very difficult to come up with a series we can compare to and see which one is greater than, which one less than. So usually, like I said, limit comparison test is a lot more practical because we may have something that messy. All we need to do is just take the highest power on the top and the highest power at the bottom. That's all we compare to. Right? So now we compare to this series. K to the 4th, 2k to the 6th. Yeah, take the highest power. Just take the highest power terms and we'll end up with that. Now cancel out, we have 1 over 2k squared factor out the 2. Now, that one, the P series, P equal to 2, convergent, multiplied by 1/2, still convergent. So this is convergent. Yeah, P series when P equal to 2, greater than or equal to 1, and multiplied by 1/2, it is still convergent. Now we know that is convergent. So actually what we compare to, by the way, limit comparison test, we could relax, we could compare that with the 1/2, or we don't compare to the 1/2. We can completely ignore it, and we can just choose the 1/k square. Let's just go with that. Like I said, the coefficient here doesn't do much to the series. So we can compare to that, or we can compare to just drop the 1/2. It doesn't matter. We can just compare to this. Now, what we do next is we will check the ratio of those two terms. Like I said, don't have to worry about which one divided by which. We're just going to divide them and see what happens. Right. Now we'll check the limit. And let this one be a sub k, and that one be b sub k. Yeah, just divide them. A sub k, that and then b sub k is 1/k squared. Right. K go to infinity. Multiply reciprocal. Want to flip that and multiply straight across, we will have k to the 6th power 2k to the 4th plus 3k squared over 2k to the 6th minus k plus 5. Right, of course when we're trying to find a limit, just take the highest power, right? And when the k to the 6 cancel out, we just have 1/2. Right, now 1/2 and 1/2 certainly between 0 and infinity. Right, so 1/2 is between infinity and 0. Yes, so we have that one check. So in that case, the series a sub k and b sub k behave the same. This one convergent, so is this one. So a sub k and b sub k behave the same. And we know that b sub k is convergent. So is a sub k. So that is the limit comparison test. Slightly more complicated than the direct comparison test, but it's more practical because when we compare two, just ignore everything else. We don't really need to see which one is greater, which one is greater than the other. Right. So since we can actually compare to this, and this one is convergent, because P series P equal to 2 as well. Right. So the trick here is when we compare to a series, we pick a series when we compare to that, it's kind of convergent or divergent. Remember, both of them diverges, both of them converges, both converge, both diverge. So that means we kind of have to know the answer already, so we can compare that to a convergent series or a divergent series. Right. Now, that brings to this example. What do we choose to? What do we compare to? If we have something like this. Right. So, before we say it, Ln of k, the ranking of Ln of k, once again, is less than any power function. So we could compare this to put k on the top, or square root of k on the top, or 1/2. It doesn't matter. But, so, now here's the problem. We have 1 over k squared. This one is convergent. And 1 over k, this one is divergent. Because of harmonic series. Right, so we can put k over k squared. Right, that the same as 1 over k. Now, the problem with this is the Ln of k is actually between 1 and k. So we know that Ln of k is less than k, any power of k. I mean, it should be grow slower to infinity. So technically we should use this, but it's also less than or equal to. And Ln of k certainly will be greater than 1. So the reason I know that because Ln of k look like this, and so Ln of k, and this is y equal to k is x though, and then 1 is this one. So Ln of k is between k and 1. No, it is in between those two. Now, so it is bigger than convergent and less than divergent. This is one of the worst. We cannot really say anything about that. Greater than convergent, cannot make any conclusion to that. Less than divergent, well, we cannot make anything about that either. So that's why this one is a little more difficult. However, from experience, like I said, it works for any power of k though, right? So any power of k. So not only less than k, it's also less than 1/2 or 1/3, any number. So let's take a look at the graph. Function. Right, we talk about Ln of x. And square root of x. So the first one, Ln, and the square root is going to be greater. Like I said, any power will work. So in that case, if it is 1/2, then we simplify this. Move the k to 1/2 at the bottom, becomes k to negative 1/2. So give us k to the 3/2. Now that k to the 3/2 is actually convergent because that is bigger than 1. So this one is convergent. And yes, we see that it is less than convergent, so this is convergent. Yeah, so if we use the direct comparison test, we will compare to this series of that term because that is convergent. Or if we use the limit comparison test, we still compare to the same series. So like that, we could compare to this. But we difficult to choose. But when we choose the k equal to 1/2, it actually convergent, and that certainly works. Right. Because whatever the series we compare to, it kind of have to behave the same as the series that we're trying to prove, which we don't know yet. So this is a good case study about when we have the ln of k, what should we do? Like I said, we can choose any power of it. Previously, we choose k to be 1, but of course we can choose k to 1/2 or any power will work. Right, so what we compare to is, we compare to this when the top is square root of k. This equal to move the k to the bottom. Turn to negative. And this is a p series where p equal to 3/2, which is convergent. Anything greater than or equal to 1 in the p series is convergent. So we actually compare to this. Now we actually use the when we know the series we compare to, direct comparison test will work a lot better than the limit comparison test. But we use limit comparison test anyway. So let this be a of k, and this be b of k. And take the ratio as k goes to infinity. Right. Multiply reciprocal. And that cancel out, and so we have k to the 1/2 at the bottom. Or I move this to the bottom, becomes k to negative 3/2. And combine the power 2 minus 3/2 is 1/2. Right. Now put infinity in there, infinity over infinity. So this is infinity over infinity indeterminate. So In order to find the limit, we use the hospital rule. And derivative ln of k is 1 over k. Derivative of this is 1/2 k to negative 1/2. That is derivative. Alright. So 1 over k, and the k is negative 1/2, move to the bottom. And multiply reciprocal. And we flip that, and then we simplify. And when we simplify, we have 2 on the top. Move that to the bottom and subtract. Same thing we did. I'll kind of run out of space here, so I'm just going to say k to the 1/2 at the bottom. Now this one goes to 0, right? Because the top is finite, the bottom goes to infinity. So this one equal to 0. Because we have finite divided by infinity. Alright, so that one goes to 0. Now, we will go back to this. Because this is equal to 0, meaning that the bottom is bigger than the top, right? So this is equal to 0. So because of that, we can say h of k is lower to infinity than b of k. And b of k is convergent. So is h of k. Right? So this is the same as the road rate. We compare the road rate of h of k and b of k. And because it is equal to 0, the bottom has to be bigger than the top. And the bottom, b of k, is convergent. So the top less than convergent is also convergent. So that this actually is the same as the direct comparison test. But the direct comparison test will take less work than this. So if we use direct comparison test, we don't have to go through this limit. We're just going to use that. Anyway, so because of that, so h of k less than convergent, so it's also convergent. So this is number 2, and this is number 1. b of k is convergent, and h of k less than b of k, so h of k is convergent too. So 1 and 2 implies h of k is convergent. So usually when there's ln, we have to kind of a little more complicated than the others, because n of k could be less than any power of k, so we have to choose the right one. But other than that, yeah, this is limit comparison test, or we can just compare them directly. Right, let's look at more examples. Right, this one. Now if it is polynomial like this will be very easy. Highest power on the top, highest power on the bottom, compared to that. So certainly we can compare to where we just take the highest power on the top, highest power on the bottom. And simplify. We did plenty of this, right? 1 over 2k. And of course we can take the 2 outside. and this is harmonic series which is divergent. So we can compare to 1/2 times that, but remember we have similar term here. Even though there's 1/2, we can just ignore the 1/2, just compare to the series without that. Right. So, like I said, you can just ignore the 1/2. The math will work just fine. So we'll compare to 1/k. And this one is divergent because of harmonic series or because of the p series with p equal to 1. Anything less the p less than or equal to 1, it is divergent. Right. And this is b sub k, and that is a sub k. A sub k. Right. Then we'll take the ratio. Divide fraction is multiplied reciprocal. I don't know why I write like that. Multiply reciprocal. Multiply to the top. Now, the limit of that is equal to highest power on the top, highest power on the bottom. Now, so this is equal to 1/2. Kind of like what we did earlier with the comparing rate. If this is equal to 1/2, meaning those two have a compatible rate. If they have the comparable rate, one of them is divergent, so is the other one, right? So if you can actually compare this to in terms of ranking the terms, that certainly works. And so this is 1/2, and because 1/2 is between infinity and 0. So the behavior of a sub k and b sub k will be the same. Or we say they have compatible rates. One of them is divergent, so is the other. So when we have a finite number here, we can say they have comparable rate, or behavior of the series are the same. And so we have they behave the same, and B of k is divergent. Usually by default we don't need to write the limits. So B of k is divergent. So the series A of k, this one, is divergent too. Right? So now that all kind of come together, right? So the rate that go to infinity actually is related to convergent or divergent. If it goes very fast to infinity, then I mean, if the bottom go fast enough to infinity, then the whole thing will converge. If the bottom go too slow, then it will not be convergent. Right. So this kind of the same thing as before. Right. Now this one a little different. What we actually compare to. Right. But whatever it is, 2 to the k power exponential function is way bigger than power function, bigger than ln, and that's certainly bigger than 5, right? And also 3 to the k is way bigger than power function, bigger than ln, certainly bigger than sine of k. Sine of k, the biggest values for sine of k is 1. By the way, the reason I have the 2 here and the 3 here, because when k equal to 1, I put 1 and 1 here, we start with 6. Sine k, sine of 1, it's not 1 degree, it is 1 radian. Alright, so it's positive. It doesn't matter though, because limit comparison test or direct comparison test, all the terms have to be positive. So I will not have, we cannot do something like, because sine potentially be negative, so we cannot use the comparison test for this series, because that potentially be negative, so that doesn't work. Anyway, so we compare to this. So we compare to the series where we take the highest power on the top, right. I guess I should say, since 2 to the k is significantly bigger than 5, and 2 times 3 to the k is significantly bigger than 1, which is bigger than or equal to sine k. Right? So another way to say this is that term is, the 5 is negligible compared to 2 to the k, and the sine k is negligible compared to that. So we just drop it compared to this. Right, and we can take the 2 outside. Or not, it doesn't really matter though. Not really matter. And then we have 2 to the k, 3 to the k. As mentioned before, whether we have the 1/2 or not, it doesn't matter in the calculation. But usually we drop it, so it's easy to see. Now, what kind of series is this? Certainly it's not a P series, right? So what we actually have here is the geometric series. Right. Remember, earlier we mentioned that this in 10.2, this is the geometric sequence, not geometric series. The geometric series actually is in section 10.3. And so, just say, now we just compare to this. Whether we have the 1/2 like that, it doesn't matter. But I will write out the important fact here. We call geometric series. Actually, for geometric series, this goes from 0. And this is convergent. If k absolute value of k is less than 1. So that's what we have. Right. And furthermore, when absolute value of k less than 1, we do have the sum like that, right? Let me find that in the note. Right. Geometric series. Yeah, when r less than absolute value of r less than 1, we have that. Of course, if this is it has equal to something, it will be convergent. In section 10.3. Right. So we actually compare to a geometric series this time. And that's because of 2/3. Whether we have the 1/2 inside or not, it doesn't matter. What important here is the ratio. What important here is the ratio. Absolute value of the ratio has to be less than 1, which is the case here. So it's good. Right. So let's properly write it out. So we actually compare to like I said, I dropped the 1/2. It doesn't matter. So this is a geometric series, not geometric sequence. By the way, the difference here is here k equal to 0, here k equal to 1. Is there a problem with that? So actually it doesn't. The reason being, if the whole series is convergent, take out the first term, still convergent. So the first term does not determine if the whole series is convergent or divergent. Take out the first term doesn't do anything. So that's why missing the first term is still fine. Or the first few terms still fine. So if we have something that is convergent, we can add a small constant to it. We can add a constant to it and does not change anything. Does not change convergence or divergence of the sequence. So we start with 1, we start with 2, doesn't matter. Missing the first few terms, still convergent. Right. So this one is convergent. Because of geometric series. With r equal to 2/3. If r equal to 2/3, and of course that means r is less than 1. So satisfy that condition. Right. And then so whatever this is going to be b sub k, and that is a sub k. and we take the limit of a sub k over b sub k. Big fraction. So a sub k over b sub k, I write b sub k first. And a sub k right. I'm going to distribute the k in, so but the top still 2 to the k plus 5, 2 times 3 to the k plus sine k, and 2 to the k, 3 to the k, and then we flip. And then we're going to flip. Right, this should be a mess. However, just like what we did before, 2 of k is too big compared to 5, so 5 is negligible. So this is negligible. So that's a lot bigger than 5. And 2 times 3 to the k is a lot bigger than sine k. So we can just ignore those terms. So it will be easier to do the limit. So we cancel everything, we just have the 2 at the bottom, or 1/2. Now, if it is equal to a constant, a finite number, what did that mean? If it is finite, meaning that they have the comparable rates, so behavior will be the same. Since b of k is convergent, so is a of k. So in terms of ranking, it worked just like that. So because this is a finite number, a constant, so they have the same rate, or we just say the behavior of the series would be the same. By behavior, I mean about convergence or divergence. So a of k and b of k behave the same. And we have b of k convergent. So a of k is convergent too. Right. So that is the limit comparison test. I said sometimes it's difficult to determine which one is greater than the others, but we can take the limit to compare the rates. If they have comparable rate, then both of them converge or both of them diverge. Or sometimes we divide and that equal to, could be 0, could be infinity, depends on the scenario. If it is equal to 0, the bottom could go faster to infinity. If it is equal to infinity, the top go faster to infinity. Compared to the others, right? So, like I said, think about this in terms of growth rate, and we have this in handy, so we actually can compare to. So, that is the comparison test. So, like I said, most of the time, the limit comparison test is more common and a lot more practical than the direct comparison test, because sometimes we compare two, we don't know if which one is bigger, which one is greater. For example, this one, we clearly don't know if this one is bigger than this term or not, but we know that the behavior, both of them will converge, both of them will diverge, because the limit is equal to a constant. The limit of the ratio equal to a constant, right? So with that, we finish section 10.5. See you in another video in Calculus 2. Thanks for watching.